right, good to see everyone. And Adrian and Foxglove team, thank you for the invitation. We're huge fans. You've saved us a lot of time and a lot of headaches. We're very appreciative. All right, I will be talking today about our journey towards automation of the construction industry, and particularly the heavy machinery. And then we figured it would be fun to look at some of the sausage making behind the scenes on what that actually looked like, not just with a summary of where we are today, but going back to day one and what did it really take to bring up a machine. We're about a year and a half old, maybe a little bit less, and made a lot of progress in that time. Some of those lessons might actually be, at the very least entertaining and maybe even educational, but we certainly had a good time reminiscing about some of the old space. All right, here we go. That's some of our machines. So we're developing advanced autonomy for specialized heavy machinery. We're starting with construction equipment, but this type of approach applies to these types of specialized equipment in other spaces like agriculture, lumber, mining, garbage movement. We chose this industry because the US is hitting this pretty unprecedented need to build. The amount of volume of construction and manufacturing, data centers, energy, housing shortages, infrastructure repairs, it's hitting unprecedented levels, and it's happening at a time when the labor pool is actually plummeting. The average age is getting to 50. 40% of construction workers are retiring in the next 10 years. And so you have this crisis where there's just not enough supply to meet the demand. When that happens, prices go up, work doesn't get done. You start to really feel this radiation across the whole economy, because this obviously stands up every industry. It's not an isolated industry. And so the problem itself, we actually started to notice a few years ago when many of us that are at the company were still at Waymo. So this is a little bit of our origin story. So I was at Waymo for about 5 years, and myself and a lot of our team, we were leading the autonomous trucking program and then various technology teams that supported the Jaguars launching in San Francisco and then later on freeway driving. This is a pretty fascinating problem. It's considered one of the holy grails of autonomy, obviously, and it's actually working. If you guys haven't tried it, you should try it in the city. 100 million driverless miles, over 2 million miles a week, and so it's really accelerating exponentially. It's in 5 cities, another half dozen or 9 cities at this point announced, and superhuman levels of safety. But it wasn't a straight line. This was one of those really interesting experiences where seeing the technological evolution of what actually helped solve this problem was really, really educational. And we were fortunate enough to be there from this seemingly almost like endless R&D phase to this inflection point where this started to really be a scalable product. And in the end, one of the things that really broke through was a shift from traditional robotics approaches, heuristics and search and cost functions and kind of engineered solutions into a very aggressively machine learning and data-driven approach to solving this problem and learning from demonstration from giant scale mileage. And without that, these problems are just almost impossible to solve, particularly when you get into something like downtown San Francisco. And what was most surprising, and maybe not surprising, but validating, was when making this bet and to make this shift, not only was this capable of solving the hardest problems in San Francisco and really dealing with this infinite chaos of pedestrians and cyclists and cars and intersections and hood jumpers. We had people jumping on our hoods. We actually had a rate on it. Like, it happened often enough to where you could put a rate on it, how many miles in between jumpers you'd get. And so all of that chaos kind of combined into a ball. It solved San Francisco, but then that system actually generalized incredibly well to Los Angeles and Phoenix and Austin. And then also from car to truck, where we unified the tech stacks and the technology really progressed, was able to jump across a very different platform and very different domain at that point, where data became the language and how you explain those differences. And so 10 to 15% more data, and you could get a truck to basically driverless quality. And by the time we're launching Austin, it was more than anything a validation and operations problem, not an autonomy problem. And so this became the core of how we thought about applying this to construction. And a lot of these lessons really carried over. Where in construction, you have a diversity of platforms, diversity of tasks, a lot of nuance, very similar types of flavors, but it was completely greenfield. There's no solution in this sort of a space, and it deeply required this sort of a solution. And so what we do is we retrofit existing heavy machinery with a sensor compute suite that turns these machines into autonomously capable for the scenarios that they're cleared for. that surface area increases over time, and then it can still be manually operated otherwise. And so our customers become the general contractors and subcontractors that buy and manage these machines, and we're effectively selling the labor and the services around it. And these machines are really well designed to just, to really be retrofitted in this way to turn them into autonomously capable. And so what does this give you? Now, you put these sensors on, you got sensing all around, main sensors, occlusion sensors. We have workflow camera and LiDAR, so you have complementary sensors for the most kind of critical focused areas that we're operating in. And now you have superhuman levels of safety. We can do these sort of system architectures to make sure that you have the ability, no matter what happens, you have the data source to then in software be able to deal with people, occlusions, surprises, and you can work your way towards superhuman levels of safety. And when you have this sort of information, you have this incredible information about the environment. It's not just for your work. You can also track your progress. You can analyze everything around you. There's all these secondary benefits that end up being very, very exciting for customers in the space. And you have all this information that you can suck in and leverage both for the core product as well as all these secondary values that almost come for very low cost because it's just software and you already have this very unusual amount of sensing in the environment that you otherwise wouldn't have. And you pull all this together and you're able to start to pull together autonomy, loading dump trucks, thinking about safety, all these sort of things. And this all looks really cool, but took a while to get there. And there really was a lot of sausage making. And so let's back up to day one. How does this look in the very beginning? So this is May of 2024. We get everybody, it's like maybe 10 of us together in a Airbnb in Sonoma. We sit around, we talk. Boxes were drawn on dry erase boards. They had lines in between them. They said things like controls and behavior and a LiDAR and camera. And we'd wave our hands and pontificate. We'd wonder how we're ever going to visualize our systems and debug our technologies. And then we had a lot of discussion about how do we solve this problem. And we made a decision to take a really aggressive all-in approach on the end-to-end machine learning and data-driven approach. And this is even more aggressive than what we had at Waymo, because Waymo was an evolution of a traditional system moving towards a more and more heavily ML-first system. But here we aggressively took the bet to go all in on the end-to-end approach. And this was actually pretty, it wasn't controversial, but we thought that we were taking a pretty big trade-off because the common thought was that you can get a system up and running faster with a more traditional robotics approach, have some sort of heuristics on and search for digging and so forth, show some proof of concept, start to learn. And we didn't do that. We just went all in on the data-driven approach. And we knew that it would help us in the long run. What we didn't realize that proved out really well, and we had a thesis on this, is that it was also actually the quickest approach to actually get up and running. And we were shocked at how well that worked. And so then we had this problem where you have almost like a chicken and the egg, where you're trying to get some data and learn and develop your system, but you have no hardware to do it on. And so you have to decouple your autonomy development from your hardware development for a decent amount of time, because you can't sit there and wait for a bunch of sensors to be screwed onto machines and drivers to be ridden. And so we started with a pure simulation approach. And this was our very first simulator. You see the incredible fidelity of Earth simulation on the bottom left over there. Beautiful visualizations. This is best of the best. I think we trained it from a bunch of teleoperation of a virtual simulator with idealized physics and idealized controls and incredible fidelity Earth simulation. And then we learned models off of this. And what's interesting is that while this was a pretty crude start, the architecture and the training algorithms and the infrastructure that drove them actually lasted far beyond this and is a foundation of everything we use today. So the data was completely bogus. We replaced the data as we got to real system, but the overall architecture, we were able to completely unblock our development by using this simulator we knew was totally inaccurate in every way, but the foundations held. And at the end of the day, we were learning to learn. And that was a pretty pretty satisfying kind of experience to then, see this down the road actually prove to be very useful. In the meantime, we were bringing up hardware by October, so May, June, July, August, September, so less than 6 months in. We have excavator. This is a 336. It's an 80,000 pound excavator. So that's kind of the low end of the mass excavation class. And these are really fun to drive. It's like everybody got a chance to drive them. And you get in one of these, like your inner 6-year-old comes out. It doesn't matter how proper and sophisticated you are. You get in there and first thing you do is you take a big clump of mud, bring it up high, and then drop it from 15 feet up and see what sort of pop it makes. Without fail, no matter how mature somebody pretends to be. It's amazing. And so we upfit these with initial versions of our sensors, IMUs, GPS, all the compute kind of behind the back seat. And we start to collect data. We start to think about the integration. Now, what's nice about these systems is that they're really nicely designed, already drive-by-wire, and so we could effectively hijack this machine, and all of the signals are going from the controls to the machine. We could pass them through if we're just data collecting and logging, or we hijack them and create our own signal, and the machine doesn't realize that signal isn't coming from the joystick. And so this started really working in October, and we could start to collect data. And the data is not just our signals, but also 100 signals from the machine. So we're collecting information from the IMUs and the encoders, every single thing passing through machine, seatbelt sensor, everything. And then first integration testing. So humble beginnings. We're sitting there with a cardboard box, trying to get this stuff onto a machine. Suddenly, you got to worry about weird things like pose and controls, and the world doesn't break up into little clumps with no resistance. And so now we're dealing with real world conditions. And then pretty shortly afterwards, we try to do our first integration of doing a first scoop in the real world. And everybody knows your first integration works immediately. It's just flawless, right? So, all right, so here we go. First autonomous scoop. We got this. A little shaky. Ooh, okay, this is weird. Resistance, it's kind of doing something. And all right, we got 10% of a scoop. That's good. And so now we're realizing, all right, you got to deal with controls reacting to the ground and the physics of everything, and the behavior model jumps around all the time, and suddenly the system has to adapt to it, and you're dealing with with the real world. And so, but this was a great start. This was November, and then only 1 month later, with work across both the ML side, the system side, and platform side, you start to get into some pretty compelling functionality. And this previous one was only about an hour of training data. I forgot to mention. This is about 10 hours, where now this is a toy example that we're using as a motivation to really exercise the whole stack, and we're trying to dig a little trench in a particular shape. But in only roughly 10 hours of training data, we're able to start to have a machine that is digging in a pretty compelling way. So it takes as an input all the sensor data, computes the pose of the arm, and then you see the purple, that's the output of the behavior model that's basically telling it how to dig. And it's kind of cool. It's it's actually working. We're really excited at this point. This is just well under a year, and with only 10 hours of data, we're able to start to get some pretty decent functionality. We're still seeing a bunch of things that are a little bit off. There's jumpiness. There's still some controls issues, but it's getting pretty compelling. And then we start to ramp up into more and more interesting applications. So now we're trying to move towards a little bit away from the toy examples and trying to go into real work. So this is trying to simulate a little bit of trenching, which is very common for laying pipes or utilities, or burying things, or whatever you need to do. And so here it's digging a little bit more intentionally a trench. We have a goal that it's set to dig to, and then we really start to think, all right, how does this come together into an actual target for a first product? And so we need a goal for the first kind of beachhead, because the whole idea here is that we want to go to market, do something very productive. The benefit of this space over something like autonomous driving is that we can actually go to market with a really great capability in certain types of tasks. And it's okay if you don't know yet how to do demolition at the same level, or handling pipes, or doing more machines. Whereas in San Francisco, you have to solve everything, because your long tail is everything. It's safety, it's the hood jumpers, everything you have to deal with. And so then we started really looking at real sites. This is like Manuel. This is like one of our design partners. This is a construction site for a factory. And we started thinking about what it takes to really be able to solve a meaningful problem that can actually become a product, can become something that is operating in a field for 10 hours a day, 15 hours a day, 24 hours a day, doing real work and doesn't require a lot of supervision and a lot of constraints. And so this is what we really started to focus on, this sort of large-scale mass excavation, which is incredibly common for massive projects like data centers, warehouses, factories. Heavy civil has big elements of this. And so then we started to really think about the types of behaviors that make this up. And now suddenly you're dealing with all of these types of mixes of behaviors from loading dump trucks to raking the earth, to moving debris, to patting things down, to waiting for the next truck. And you're doing this across all types of sizes of machines, from a 40,000 pound in the 320s to the 352, which is 115,000 pounds. You have different lengths, arms, you have different physics properties, you have different bucket sizes. And so now you have the real world where you have to deal with all these aspects. And so what's interesting about the approach, this type of an approach versus the kind of traditional approaches, is that you don't get to go and create modules and state machines that say now you're going to rake and now you're going to load and now you're going to reposition yourself. You have to have a system that really absorbs everything. Very similar to how if you're going to have a behavior model that drives in San Francisco, you don't get to really isolate out models, because everything kind of blurs together. And so we decided to take a starting point here. One of the more complicated elements, which is actually the digging and loading, but also the most common. This is probably 60% of what you do on a site like this is you're just digging and loading kind of nonstop. And we thought, okay, let's really focus on loading a dump truck, and we're gonna push on these capabilities and try to optimize. Obviously, you have the safety in place that's required for interaction with the dump truck, but then try to really learn about what does it take to do this. And now, by this time, our data is ramping into thousands of hours, and it's like we're starting to get a lot more capabilities. Our tools are better, everything's better, and so we started getting into something that looks a lot more compelling than those first and early runs. This is from July, where we're doing autonomy. We have a supervising operator because we're still building out the safety system. But it's actually digging. So it's taking as input all the sensor data, the LiDAR, the cameras, all the machine signals, the computed kind of position of the machine. There's safety regions for the excavator, for the dump truck. And then again, there's an output that is the behavior model that is driving the behavior of this excavator. And this part's pretty cool because there's absolutely no lines of code that tell it how to interpret the earth, or how do you call a bucket, or or how do you change states between one thing and another thing. This is all just learned, and it's a little bit of a double-edged sword, because on one hand, this is by far the most efficient way to start to learn these types of subtleties of behavior. It doesn't matter if it's a car or an excavator or a humanoid robot or an arm. The technology really has progressed to where this is the best way to really think about kind of capturing all those nuances that are so hard to explain, and even more, they're so brittle on the tail end. But at the same time, it completely changes the way you develop these systems, because now you don't directly fix problems with software, you fix problems with data. And so now you get into this really interesting challenge of splicing your data sets, thinking about how you optimize between the different types of capabilities, and now you're slicing and evaluating the different use cases. And so here's an interesting case study where we started to see this like really interesting emergent behavior. And so we were very focused on trying to build a competency in our first target behavior, loading a dump truck. And this was working pretty well. We started to get better and better. More data meant you're better at laying out where you're dumping in a truck, how are you interacting with earth, how you interpret the world in front of you. But then something really interesting happened where we started seeing this emergent behavior come up, where when the dump truck was full, the machine started to like organize earth and kind of pull it closer to it so it would be in a better position to load the next machine. And we're like, this is almost creepy in a way. It's like in a wonderful creepy way. And so I think we kind of exacerbated this because we didn't allow the base to move here. And so if you can't move, what are you going to do? You're going to like suck in all the dirt you can so that you're in a better position to load the truck the next time. And so you have these like really fascinating engagement that start to open up where you start to see and understand the world around you, but you're manipulating the capabilities by feeding in new data, by up-sampling and down-sampling the things that are the behaviors you want or don't want, and playing with the structure of the network. But at the end of the day, it's a very, very different type of development than what we were used to. And if we go back to this world over here, suddenly, suddenly, you see all this work here. We slice up the world in human understandable ways for the purposes of evaluation and thinking about competencies. But this is all one giant model that actually absorbs all these behaviors that becomes better and better. It's no different than a behavior model operating a Waymo in San Francisco. We aggressively sliced up pedestrian evaluation and traffic lights and cut-ins and all these behaviors that are categories of things that matter. So you can evaluate safety, so you can evaluate your competency, so you can hill climb and improve the performance. But you learn a very different type of muscle where you don't get to just say, if you see this, do that. You actually have to slice and use data in this very unique way. And so this is ended up being really fun. And and so then you start to see these sort of like really nice kind of emergent, these nice emergent behaviors that we never were directly even focusing here, but we just let the system keep running, and then suddenly these things emerge. And so part of the muscle that we're building as a company is now absorbing on a faster and faster clip all this new behavior, learning about the scaling laws of how much the previous data helps you with the new types of capabilities. And then we're going to see this as we go to demolition, as we go to material handling, as we go to wheel loaders and bulldozers, as we go to completely different use cases, which is pretty exciting. And so today we are aggressively pushing on autonomy capabilities, maturing safety, ramping our data, starting to move towards larger and larger amounts of hours, learning about how we go from a world where we're trying to just get one scoop to work to where yesterday we loaded 50 trucks with one excavator on our test site. And so these things start to get better and better, and then it becomes increasingly important that you have very natural ways to measure and evaluate your progress so that you actually have a signal to hill climb on. And this is one of the biggest learnings from Waymo, is that it's surprisingly quick on how fast you go from triaging disengagements and very obvious mistakes and faults and crashes to actually having a pretty painful sparsity of relevant information, because the things you care about happens once every 50,000 miles. And so we're now at a phase where we're trying to kind of get ahead of this and work our way towards first driverless operation next year. Been an exciting journey. So I have about 2 minutes left. I figured I'd take a few questions if anybody has any, and then hopefully this was an interesting look at the 0 to 1 of an autonomous excavator.